The next reader will be Miroslav Havelka from National Radiation Protection Institutes of Czechia.
Good morning. The presented study is focused on testing the ability of radon monitors from primarily their use as a radon sensor of indoor air quality for direct ventilation regulation to achieve the recommended reference level.
Could you hold the mic?
No, it's on.
Just hold it close.
Close. Okay. For ventilation of indoor, the ventilation of indoor air can be used as an alternative radon risk reduction measure. For example, when other radon protection technology has failed, or it can be used in low radon risk area. We tested three types of sensor with different detection efficiency to determine the parameters and in reference radon atmosphere, and we also simulated sensor response to estimate their dynamic parameters during ventilation. SURO has a long tradition in calibration and testing of radon devices. For this purpose, SURO has the appropriate equipment, which also includes a newly installed generator for preparation of radon-free air. Typical radon concentration in prepared air is lower than 20 millibecquerels per cubic meters. For test of radon sensor carried out as part of this project, we use small radar chamber connected to the radon source. Both source and chamber operates in flow-through mode. Air was taken from a radon-free air generator and flow was set using Bronkhorst gas regulator. Tested devices were placed inside the radon chamber, and reference atmosphere was sampled to external box with reference monitor. This arrangement gave possibility of device testing at low level activity concentration and possibility of long time test. The main advantage of flow-through system is stability, simple formula for calculation of steady-state concentration, and direct traceability to the radiant primary standard. This is some picture, and radon concentration in atmosphere and radon chamber was calculated according to this formula. Both activity and emanation power are certified values. The float rate was defined by gas regulator. We used Bronkhorst with gas regulator with repeatability of 0.2%. The uncertainty of radon concentration has components related to certified value of radon activity, emanation power, and flow rate. Besides that, components less than 0.5% due to correction for temperature, pressure, and humidity has to be applied. If the reference atmosphere is prepared at constant temperature and humidity, practically only instability derived from changes in atmospheric pressure was expected. We measured stability using alpha gas monitors, firstly at kilobecquerels activity range. The concentration was stable, as you can see in the picture. Then we tested stability at 300 becquerels per cubic meter. From variability of measured data, we tried to estimate detection efficiency. But producer declares the detection efficiency only at 20 or 100 becquerels per cubic meter, so we were not able to correctly compare our estimation to declared value. The situation was better in case of stability measurement using FT-Lab radon eye monitors. We use 7 monitors as seen the results. It's a low-cost monitor which has a high sensitivity pulse ion chamber. We use original FT-Lab monitors. Detection efficiency estimated from variance of measured results correspond to 4 hours per 1 becquerel per cubic meters. It was in good agreement with the declared value. This finding led to use a set of 7 radon eye monitors as a reference for some tests. As an example, you can see the increase and decrease of radon concentration. We use 10 minutes data reading. This was possible thanks to Open Communication Data Protocol on original FT-Lab monitors. Radon eye monitors use as a reference is limited by temperature dependencies. Temperature increase from 21 to 32 degrees results in response decrease by 20%. Beside radon eye monitor, we selected for testing Tesla probe and Robin sensor. Both the sensors are based on principle that the activity of polonium ions electrostatically collected on detector is measured. SURO has about 80 radon eye monitor, approximately the same number of Tesla monitor, and we have two monitors Robin for testing. It's only pictures. Considering the sensor to be applied for direct ventilation control, should be able to correctly and quickly measure 300 becquerels per cubic meters at the sensor key parameters are their sensitivity, data relay constant, and stability. Sensitivity is usually declared by the producer, but usually only at one activity point. The table illustrates how important overall sensitivity is for counting time to achieve 10% uncertainty at 300 becquerels activity. Table illustrates differences between tested sensor, showing that Robin needs about 12 hours to count 100 pulses at 300 becquerels per cubic meter activity level. The second key parameter is related to monitor response delay. Assuming a known detection principle, it's possible to estimate the delay from reaching the certain radon concentration to its display. Black line is radon concentration, blue line is monitor response. In the case of pulse ion chamber, similar to radon eye monitor, with 60-minute moving average, response delay is about 55 minutes. For Tesla monitor, it's 68 minutes. Smaller delay constant has 10 minutes moving average, it's about 30 minutes. We also tested radon eye monitor. In Toron atmosphere, we found that radon eye monitor detection efficiency for Toron is about 1/2 of detection efficiency for radon. This implicates the delay related to radon diffusion to the chamber is about 1 minute. The next 3 slides relates to humidity test results. For Tesla and Robin sensor, both responses were affected by humidity. This phenomenon is typical for sensor with the same detection methods as Tesla. The next part of the presentation deals with the simulation of monitor responses when used to control ventilation. For simulation, the simplest possible ventilation strategy was chosen to reach limit 300 becquerels. The first phase was linear increase to ventilation switch on level. The second was increase to switch off level. Radon concentration decrease rate was estimated from carbon dioxide concentration measurement. You can see this. From this measurement is conclusion that radon measuring sensor have a very slow response to switching off the ventilation compared to, for example, conventional carbon dioxide sensor that can handle some aspect of ventilation much better. This slide, the next slide, the simulation of radon concentration and the response sensor are displayed. This is for Gaussian chamber, next one for Tesla-like sensor, while actual radon concentration oscillates in a range from 200 to 400 becquerels respectively. Response in case of ideal sensor with high detection efficiencies is only in limited range. This small response difference has the consequence for switching control. Only devices with appropriate sensitivity could be applied. The next slide illustrates the monitor response in case of real detector. Sometimes it looks like it can be used for switching, but simulated test of switching on ventilation proved that radon eye sensor get better results than Tesla, which often switch at of the right time. And conclusion from testing sensor, only radon eye sensor proves data suitable for direct ventilation control. That's all. Thank you for the attention.